what is this first talk about? Here we will talk about neural networks and in the end, how to implement very basic concepts with Keras. The second talk, it's about two important network architectures that are convolutional neural networks and recurrent neural networks. And the last talk, it's very short, and it's basically a guide to implement the hands-on exercises. Please don't hesitate to ask anything. So only because we are a lot of people, write it into the chat room, and when I have the opportunity to see the question, I will answer, I promise. So let me check if something is missing. No, everything's okay. Okay, let's start. So first, let's say about something about what is machine learning, neural networks, and deep learning. That are concepts that we are currently hearing everywhere. And then we will talk about neural network concepts particularly and the different topologies. And finally, let's see a little review on the use of the Python machine learning libraries. So we are interested in understand everything because we're interested in implement all those algorithms in our data. So let's discuss shortly what can we do with the data. So we are interested in different things. We want to visualize the data, we want to analyze the data, apply different classification algorithms, and we want that our algorithms be as intelligent as we can get. So, which algorithms are available currently? So we have linear algorithms where we can apply linear regression or logistic regression. We have tree-based algorithms, decision tree, random forest, or gradient boosting. And we have neural network models that are the ones that we are interested in. So if it's more easy to see it, okay, here. I want to show it in a window presentation because it's more easy. Here. Okay, perfect. So when we are talking about machine learning, we have three concepts: artificial intelligence, machine learning, and deep learning. And when we say deep learning, that is the concept that we will study in this presentation, we were talking of neural network layers. So we first have to understand what is neural network and how to implement it in different layers for our model. So why deep learning? What we have now that we hadn't had before? So we can have a data-driven approach. That means that we can apply algorithms without knowing anything prior our model. And we can learn how to identify directly different features from data. So we have low-level features. That means that if we are talking, for example, about, let's say, we want to recognize faces, what is a low-level feature? It means that we have first lines and edges that we want to identify. Then we have another level of features that it's part of the face. It means, for instance, an eye, a nose, an ear. And then we have the high-level features that it's a facial structure or a face. So data is divided in data can be seen as different level of features. So Sorry. So why can we use it, these models now? We have a lot of data, meaning big data sets that are available for us. We also have a new hardware that allow us to implement models that are massively parallelized. And we have a lot of new advances in software, meaning that we have a lot of different models and toolboxes currently implemented. So yeah, okay. So getting back on our data, we have data that we want to use. So how we split the data to use it in our model? So we have a set of data that we will use for the training of the model, and a set of data that we will use for testing our model before being applied to the real world. And the training data can be divided also into parts, meaning a part that we will use properly for training the model, or another part that could be used for validation. What is validation? It means that we want to, for example, select between different models, and we use the data, a part of it, for estimate different metrics, and we choose which is the model that minimize some value of a given metric. So it's a part that we save for fine-tuning. And finally, we use final part of the data for the testing of the model. So here you have the proper definition of the training set, the validation set, and the testing set. So now let's move to the proper neural networks. So what is a neural network? Well, it is an algorithm that it is implied in biological networks in such way that we have an input weight connection here. We have an input data. We have an operation that's a sum, and then we have a nonlinear function applied for our operation, the sum, and an output. So we take a lot of these units and put it all together to make that we will call a layer later. So what is our first model? We have something called Perceptron, and that is our structural building block for a neural network and for deep learning. As I said before, we have an input, we have a weight, our operation of sum, our node. Okay, now I think we are ready to continue. And I was about to talk about the perceptron. That's our building block for deep learning. And yeah, we have an input that is our data, weights, an operation of sum, a nonlinear function applied, and an output. So this is the block that we will use. Oh, let me show you like this, a slideshow, it's better. So here, if we use an equation, we can describe our output in terms of our input and our nonlinear function. And in some cases, we can use a bias term also, and we have our bias term plus the linear combination of our input plus our weight term. So our output will be a nonlinear function applied to our combination. That is how we obtain the output. So if we want to write everything in a vector form, we can apply this notation. And okay, let's talk a little about the nonlinear function. For example, here, our nonlinear function is a sigmoid function, but you have a different. Sorry, I have more people requesting to join. Okay. Sorry. I think it will be. Yeah. Okay. Let's continue. Okay. So we have different nonlinear functions that can be applied. And also we have each function implemented in TensorFlow. And later we will see how to use them. And here you can see we have a very large set of nonlinear functions to be used, which use will depend on the kind of network and the application, the implementation that we need. So we will discuss further which is the more appropriate function in each case. So why we need a nonlinear function? Because we need to take a nonlinear decision with the data. That's the reason that we need this nonlinear function. So here we can see an example. Let's suppose that we want to cluster the data here. So with a linear function, we cannot cluster the data because, as we see, we color it with different colors. So we have two kinds of data that we want to separate, and we need something that allows us to separate these kinds of points, but we see that there is no line that allows us to do that. I'm sorry, I still have some people requesting. And let's use the information that we saw before to build a neural network properly. So our version of the perceptron, we will write it as a simplified version here, and we will use our simplified version to obtain a network. Here, we will use two perceptron models to build two. So we have all our inputs here that are connected to all the outputs of one layer, and this kind of layer we call it dense layers, and in fact the name dense is used in Keras to describe it, just like that. We call it dense layer in the same way in the implementation. So this is a class defined in Keras and in TensorFlow. So if we want to use this here, we have our input layer, our hidden layer, and our final output. And this is more or less how you implement a dense layer in Keras. You need to define the size of the input. You need to define the number of units that your hidden layer will have, and then you need to define how many units your output will have. So if you take a look how to write the equation for one of the units, here you will see that you have all inputs combined with the weights of the connection, and then you will have an operation that we said before. Here it's a linear operation because we didn't use, for simplification, the nonlinear function. And then you will obtain the output depending on how many units your output will have. You will combine them. This is just an example. And if we have a deep neural network structure, we will have different layers where we're implementing this layer by layer, and this is how you write it down. So now that we have our structure, we need to try, we need to train the network to solve the problem that we want. It depends on the kind of problem that we want to solve, meaning that we want to use the model for prediction or for classification. Depending on that, it will be the cost function on the objective function, or sometimes called also loss function, to be used for the training. So if we want to make some predictions, or we have some regression problems, we will use, for instance, mean square error function. And if we have a classification problem, for instance, for the data, we will use cross entropy or binary cross entropy, depending on the kind of problem, the amount of classes that we want to classify. And we have different loss functions, more than that I described here. You can take a look, for instance, in this paper, how to use the different loss function depending on the problem. So let's start, for instance, with an example using cross entropy. So we have a classification problem, and we have the value that we have our data set that it consists of different sets of numbers. So given a pair of numbers, we will obtain another one, and we will to predict using that what we will get when we give to the network one set. So as our network is learning, we will have a prediction of the value. For instance, this prediction is 0.1, but the set was expecting another value, so here we get a 1. Our network predicts 0.8, but the actual value was 0. And here we get 0.6, but we are waiting for a different value, so we are waiting, sorry, for the same value, so we get 1. And here, as we will train our network, we will get probability values that are close to the actual value that we are waiting for. So we will use the sets to train the network for the task and to obtain values that we are close to the target output. Here we have another kind of problem that it's a prediction problem where we want to get as close as respected to the target output. This one was a classification problem, and this is a prediction problem where we want to get the current number. This is very different problems. So when we train networks, we want to find the weights that achieve the value of the lowest loss, and that means that we want to build a cost function, minimization. So the idea is that we want to find the ways that get us the lowest loss. So let's say, for instance, that we have this landscape where our function depends only on 2 variables. But this is just an example, because we know that we have to get all the weights in our network. So this is a very how do you say it, a pictographic example where we have a network with two weights. So we have an hyperspace where we have a lot of weights, and we want to find the lowest value that minimizes this function with respect to the weights. So let's see in this example. So we'll start with a random value of our weights, and we want to minimize the function, meaning that we want to find an algorithm to run over the values that give us the small value of the gradient. So we try to move in the opposite direction of the row of the gradient here, for instance, where the red is the highest value and the blue one is the lower value. So how do we achieve the lowest value in our function? Well, we have to initialize our network weights in some way, for instance, random. All of the values are initialized random, and we try to move and compute the gradient in each step, and we update the value of the weights using the value of the gradient that we estimated, and we keep running until we get the mean value. So, but we have to take into account that when we are looking for the values, a small change on one weight will affect the value of the loss. So this is what we call backpropagation. So it is basically apply a chain rule to our function, take into account the change of the values of the weights, and we repeat this layer by layer. So there are different ways to apply the gradient descent update, and we use different algorithms, or also called optimization values. One way to achieve that is using, for instance, different algorithms that currently you don't have to implement from zero. You can use them using the TensorFlow functions. For instance, one of them is called stochastic gradient descent. Another is called adaptive stochastic gradient descent. You have a lot of ways, a lot of algorithms. Each implementation is followed by the paper and the explanation of how it works. So you have a lot of reference and very good documentation about the method that you are implementing to obtain the minimum value of the gradient and optimize the network weight. And when you do all of this, you obtain the better model for the network. But the idea is that you want to obtain an ideal fit. You don't want to obtain a function that underfits your data, or you don't want also to obtain a function that overfits your data. That means that it cannot be generalized. So to do that, you have different methods that you can use called regularization methods. It consists of a set of things that you can do to avoid the complexity of the models. And all of these things you can use to generalize your model to be able to predict the unseen data. Some of the methods, for instance, one of them is called dropout. It consists of randomly set to zero some of the units during training. It means that you disconnect the weights of those units, Another regularization method consists of stop. Sorry, I have a comment, I think. Sorry, I came back. Okay. So another regularization method consists of early stopping, and it means that you monitor testing and training data, and you stop the epochs of training before the model of the testing and the training samples separates. Well, let's make a short summary of this part. So we have our basic model, that is the perceptron, where we will call it as our structural building block. And we have our nonlinear activation function that allow us to make a nonlinear decision. We have our networks that are made of layers of different units, a different number of units, and we optimize our model applying the method called backpropagation. The idea is that we apply in the practice an adaptive learning rate method to obtain the minimization of the gradient. And we have different ways to regularize our problem that allows us to do not underfit or overfit our model. So now let's talk a little about the kind of topologies that we will meet. So let's continue with the recurrent neural networks. I said before that we have this kind of network coded like that because part of the output is reinjected in the network. We have different topologies that are recurrent, that are currently used in machine learning. We have the simple model. We have a long short-term memory, and we have the gated recurrent unit. These two have different implementation that allow to solve a problem called gradient shrink or gradient explode problem that is related to the training method. When you train using backpropagation through time, we will see later, we get some problem with the recurrent neural networks simple model. So there are different solutions implemented in new configurations. So the idea is that this class of networks are used to exploit the sequential nature of the input. The inputs of the networks are text, speech, time series, and everything else that can have the occurrence of one element in a sequence depending on previous elements. About the convolutional networks, yeah, sorry, let's show it as slideshow, it's better for me. So convolutional networks are used with convolutional and pooling operations applied to the data in the input. They are very sophisticated models that allow us to extract different features of the data, particularly in machines, and naturally allow us to make different levels of abstraction in the data. We can think on these networks that we have an imaging in the input. We have some convolutional and pooling layers that we will see further how they are. And we have, sorry, okay, and we have a, sorry, and we have the output, like could be different, for instance, it could be a label classification, or could be data for, let's say, if we have a crystal orientation or something that is relevant for our research. We have images, and the objective of this implementation is to obtain some features that characterize our data. So let's talk a little about how we use and implement everything that we saw, because we saw it, because we saw it in a general and abstraction level, and we want to implement everything in our computer now. We want to use it to model our data. So first of all, as everybody who asked me in emails and stuff, first of all, I think you could install a virtual environment in your computer to use Python. If you are not able to do that, you can use Google Cloud Service, or for instance Google Colab, that I will use to show you the exercises, or other service. You can install all the libraries. One option is to use Anaconda distribution package that includes TensorFlow, and here says piano, but currently right now it has also TensorFlow. And someone is asking me for the links. I will give you. Yeah, we can use Colab. Yes. Someone is asking me. We will use Colab. It's very easy, and I will show you when we finish the presentation how to use it. Uh, Actually, I will tell you something. My computer broke 2 days ago, so I'm using a borrowed computer, and I don't have all my things installed here. And I'm currently using Google Colab for this workshop and the tutorial presentation. So you will see that it's very easy to use and to implement everything that we learned today. So, but if you want to go to the process and install everything in your computer, you can do it. One very nice option is Anaconda package, but there are others. And maybe you will be familiarized with some of the scientific libraries such as scikit-learn. It is very useful. I love the charts that it shows. For instance, I get this one from the website. It starts by showing you what can you do depending on the amount of data that you have and which are the algorithms that you are able to implement. So it is very interesting. You can go and use it. And let's start to implement some of the things that we learn. One of the ways is that you can do it from zero with math, libraries, and Python. I recommend that if you want to learn very slow and nice, you can implement every neural network that we saw from scratch using Python libraries. But if you are in a hurry or you know some of the knowledge that we saw today, you can use the dedicated open source framework that we have available, such as TensorFlow and Keras. I didn't comment it here, but you have also another choice that is called PyTorch. Maybe some of you is currently using it. It is okay. It's very nice also, but I will stay on TensorFlow and Keras today. So, what is TensorFlow? It is an end-to-end open source platform for machine learning that have a lot of tools and libraries. And the interesting thing is that you have a very nice documentation that you can use with a lot of examples. And the community that is currently using is very large. It's not only people from machine learning field, it is also people from different neuroscience uh, fields that it's using it. So what is Keras? Keras is something that it's running in a high level from the basic calculus libraries that it's, for instance, TensorFlow or another ones that were older like SCNTK or Piano. The idea is that you have already implemented everything that we discussed before. You have layers for recurrent neural networks, for feed-forward networks, and also for convolutional and other configurations. You have already everything implemented, and you can make your models by adding layers of whatever you need to build. So it is very nice. Currently, right now, Keras is part of TensorFlow. It will depend on which versions you will download, that you will have inside TensorFlow the Keras libraries implemented. So you have a very nice guide to see what can you use inside TensorFlow and which are the basic advantages that we have. Sorry. Keras is a very modular API, and you can implement everything either in a sequence or in a graph of stands models that you can combine like if were Lego blocks. The libraries allows you to implement cost functions, optimizer, different initialization schemes, different activation functions. You can go and pick it up, whatever you need, that it's already written, but you can also write your own functions and implement them. So actually it's very flexible. So if you do not find whatever you need, you can build it. So because of that, it's very easy for extend everything that you need. So as I really like this kind of charts, so you can go and take a look that you have here. This chart for Keras, for instance, you have basic examples and how to configure your data to be used. The different, for instance, processing and training algorithms. You have the layers, you have a lot of things that you can take a look, and you have the code examples to be used. So now let's implement our first model. So let's say that we want to implement a sequential model and give to our model a set of layers that we want to implement. Just we will build the model. We do not train it on anything. Just let's build it. So first of all, I think everybody is a little familiarized with the use of Python. So you know that we need to import the libraries that we will use. This is this part. And now we will build the model. You have different ways to build a model. One is this one that's called here sequential, and you put everything inside of the model. Or you have another way to build it that is, for me, it's more natural if you are learning, that is to build your sequential model in one line and add whatever layer you need. So here you are adding a dense layer, such I described it in our presentation here. And here we have 32 units, and we describe the dimension of the input data. And then we choose which is the activation function, the nonlinear activation function that we were using. In this case, we are using Prelude, but we can use whatever you want, hyperbolic tangent or whatever you need. So here we have our model implemented. So if we want to check a little more on these slides, material will be available on the website that I prepared. And if you want to check the references, there is a very interesting online course that I took a little ago from MIT that is very, very nice. And of course, you have to take a look to the TensorFlow website and the Keras website. They are very, very, very nice and well documented, and I recommend to go there and take a look. So this is everything for the first talk. Please, if you have questions, address it now, and then we will move to the second talk. In the second talk, I will discuss a little more on recurrent neural networks and convolutional neural networks. Okay. So you have questions? Okay. Here. The visual cortex recurrency is also special in the sense of autocondition. The question. Does anybody know recurrence architecture for special temporal interaction? Okay, I don't know right now, but I could think about it. I know that some people is using convolutional neural networks to process temporal information and otherwise, but it depends on which is your motivation. If you want to describe what is happening with the visual cortex, or if you want to process imaging data, it will depend on that. So let me understand the question. What do you want to know? Which is better for modeling the cortex, or you want to know which is better for imaging processing? In a big way, I will change the slides for the cortex. Okay, I'm not sure because okay, I'm not sure right now because there are very different models for describing the visual cortex. So this is not my field of expertise, but yes, yes, I understand. I understand. I think that is why convolutional neural networks are better to be described. You will see it in a minute. So I will stop sharing this one. I will share another couple of slides. So just give me a minute. Here, share screen. Let me know if you can see properly the slides. I cannot see, sorry, I cannot see the chat window, but just give me a minute. Okay. Just a minute. I lost the chat window.
And we can see the slides. Well.
You can see slides. Thank you so much. Here. I found the chat room. Perfect. So, perfect. Okay, let's continue, and I will think about that because it's not my field of expertise. So, now let's take a slide show. Perfect. So what we will have in this talk, we will talk about recurrent neural networks, convolutional, and some motivation and application of each of these layers. So what about recurrent neural networks? We have a sequence that we want to predict the next element on the sequence. This is more or less, in general, what we want to do. So which are the applications where recurrent neural networks are used? Well, we have a sequence text prediction, data that correspond to time series in general. Of course, it is very used large in speech, and also it is used, and I use it to describe models that are used for the cortex and prefrontal cortex and different brain areas that show a high recurrency in the connections. So we have two motivations to understand this kind of networks. One that it came from the part of machine learning field, and the other one that correspond to the part of the neuroscience community. So we want to handle variable lengths of sequence. So we want to that our model be able to handle a sequence of variable length. We want to track the long-term dependencies on our data, and we want to keep information regarding order, and we want to the parameters be shared, the model parameters be shared along all the sequence. So basically, recurrent neural networks are the most common approach to model sequence problems. So we have different input-output configurations for the recurrent neural networks. So we have one input, one output, many inputs to one output, or we have many to many. It will depend on the task that we are interested for. Here, I put some example task. So basically, we have our input that it's a temporal sequence, and our output vector. So we have something called hidden state, HT, that will affect the following value of the output. This is what we call the recurrent cell. And we apply the recurrent relation at every time step to process the sequence. So we have the hidden state, that it's our function, our nonlinear function, applied to the state of to the value of the previous state, and the current value of the output. So the idea is that we will use the same function and the same set of parameters in each time step of the sequence. So we build our output as an value of an output matrix applied to the hidden state, and the hidden state, in this case, we choose to apply the hyperbolic tangent as a nonlinear function. So we have our recurrent matrix and our matrix applied to the input. So this is the input, this is the matrix of the input weights, and this is the matrix of a recurrent weight. So as you can see, the output depends on the hidden state, previous hidden state, and also depends on the input. So the basic idea that each one of these cells could be unrolled as each time step using the same set of parameters. The same for the recurrent matrix. So we have all the same parameters for all the sequence. And the method that we apply to obtain the best parameters is called back propagation through time. It is basically the same idea that we had when we want to train networks, feed-forward networks, but in this case, we have an additional problem, that is that when we apply chain rule to obtain the minimum value for the, to build the gradient and then to apply the minimization algorithm, we have to take into account that it will depend in the value of the time steps here. So this generates some problems call it a vanish gradient problem, and it will generate a problem that it's when you have a long-term or short-term dependencies, meaning that the time steps that are closer or farther from the points that we are seeing in the sequence, we have to be very careful. So some of the things that allow to solve the problem of the gradient and the chain rule are used particular activation functions. For instance, one that is very common to use for recurrent neural networks is ReLU. Another way is to be very careful in the way that we initialize our recurrent matrix. One way is to take initial values as identity matrix. And another idea is to do not use a recurrent neural network directly as I described it before. Instead, using a more complex recurrent network architecture, for instance, gate recurrent neural networks or long short-term memory networks. Basically, these configurations have mechanisms that control the back propagation through time because of the gates do not allow of the problem of the gradient to propagate along the network. So if we summarize this part, recurrent neural networks are very, very good and suitable for sequence modeling. The idea is model sequence through a recurrence relation. The way to train them is using back propagation through time. And we have new configurations or architectures that allow us to model long time dependencies in a better way. These findings are for 2014 and stuff. And using that, we can model music generation, sequence classification, translation, and other different tasks that are related to time sequence. So let's talk a little now about convolutional neural networks. So one thing, if you have a question, please do not hesitate to write it in the chat room. I will take a look to the chat room later. I'm trying to see it right now, but I cannot see it. It keeps moving from the screen. So let's continue. Okay. Sorry. Let me put it as a slideshow here. Okay. Convolutional neural networks are currently the most used computer vision model. So people is using it for face detection and recognition. Also, it is using this technology for healthcare, medicine, and biology. And it is the basic part for a self-driving vehicle. Whatever you want to say about vehicles, it could be cars or drones or whatever you want, because you need to detect context information, and they are very good to do that. So what do the computers see when we see that computers are able to see? So we have here a black and gray and white image, and here we have actually a set of numbers. So we have a matrix representing each pixel and a number representing the intensity between the white and the black values. In this case, from 0 to 255. But in case you have a color image, you have also 3 numbers representing each value. So which are the tasks that are common in computer vision? We have regression, we have classification, and we have the problem that I described before as an example, that it's a high-level feature detection. We have to we want to detect particular structures that we are interested in. Let's say in healthcare, we could be, for instance, a tumor or whatever you want to identify as a high-level feature. Again, we have our low-level features, in this case, our lines and edges, middle-level feature, and high-level feature. So our structure of networks will identify automatically different level of features in each layer. So we have a fully connected network, and we have an input that is, for instance, a 2D image, and it is represented with a vector of pixels. And here we connect the information to the hidden unit, and we don't have a special information here. We have many parameters. So how can we use the spatial structure in the input to inform the architecture of the image to the network? That's the basic idea. So how we use the spatial structure? An idea is to connect parts of the input to the neurons that are, or units that are in the first hidden layer. And the idea is that each unit only see a patch or a part of the image. So as we see, we have to connect each part in the input layer to a single unit in the following layer. And then we can use a sliding window to define the connections. So we will see it in a minute. How can we weight the patch to detect a particular feature? So let's say that we define a filter, a 4x4 filter, where we have the 16 different weights, and we apply the same filter to patch in the input. And we move 2x2 pixels at the time. So we apply the set of the weights to extract local features, and we can use multiple filters to extract different features that we are interested in. And you will see that spatial information is conserved, it is saved along the network. You will see how. So let's suppose that we want to compute a convolutional operation of this image. Let's say that this is our input image and this is our filter. So we slide this filter over the input image. We multiply element-wise, and we sum the values of the output. In this way, take a look. We operate this part, and then we move the slide here, and then we move it here, and one by one, we are obtaining something called the feature map as we move along all the spatial structure of the input. So we obtain our feature map, and we can choose to apply different filters depending on which is the feature that we are interested in. So how we apply this for image classification? We have our input image, our convolutional feature map, operation called max pool, and our fully connected layer that allow us to get a classification of the categories. So for each of the layers that I described, we have implemented the corresponding function on Keras. So the idea is that a pooling layer that I described allow us to downsample each feature map. So the idea is that we train this model using images, in this case with a label. Each image has a label because we want to classify them into different categories. So the idea is that network learn the categories using the data set. So we have here, as I explained before, but now we have how to do it with the map. And the idea of pooling is to obtain, here we have implementation, the idea is to obtain in each of the set, for instance, the maximum value. Max pooling is this. So we have our feature map, and now we obtain the maximum value of each one. This is a way to reduce the dimensionality of the feature map and to save in some way the spatial invariance. So again, we have our feature detector. So in the first layer, naturally, we get the edge or the dark parts. The second one, we get the middle level extractors. And finally, again, we get the facial extractor. It will depend on how high are the features, how high level are the features that we want to detect, how many layers we will need to implement. But let me say to you that it is already a lot of, there are a lot of systems that are already pre-trained, and they implement different libraries of data to obtain classifiers for images. So it is not that you have to start from scratch every time. You can use that already it's available. So what is the idea of using convolutional neural networks? The idea is that we can represent images through a feature map. And then we can represent the images using those maps. And this is the basic knowledge that you need for computer vision. So we have these kind of networks mostly apply for classification, but they are also applied for other stuff like segmentation of an image, control or other operations, for instance, related to security or things related to identification or also robotics. So convolutional neural networks are used for a lot that is related to imaging detection. So now that we know which are the networks that we need to understand how to process images, let's talk a little about the standards of the data sets that are used for learning and training, and also that are used for to obtain the, I'm sorry, I forget the word, but it means when we want to obtain a benchmark, sorry. We want to compare different networks, and you want to get a benchmark, which is the better system. These things that I will show you in the following are the standards that are currently used. So one is the MNIST dataset, means dataset, that it's a set of labeled handwritten digits that you can use for image classification tasks. Then you have another more fun data sets. This is the fashion MNIST, that it's closed, and it is also a labeled data set that you can use for training your visual recognition systems. And then you have a Cipher data set that it's a very, very large data set with a lot of classes of images, all of them labeled, that you can use also. Another one is ImageNet, and you can go download it and use it in all of your systems. They are here on the path of each one, and you can use it for training and learning a lot with these networks. Actually, we will use the handwritten dataset for the hands-on in some minutes. So if you have any questions, this is the second talk. Please tell me now. I want to find the chat room. I'm hearing someone.
That's me. Hi again. So you cannot find the chat window?
No, sorry,
because there are many questions there.
Okay, I will address to them, but just give me a minute because I can see you. You know, it's the worst when it is not your computer.
Yeah, I know. Perhaps you can stop sharing your screen. I don't know if that will help.
Yes, I will do that for a minute because, okay, let me here. Your screen is paused. Perfect. I have paused the sharing. The screen is paused. Stop sharing. Okay. Perfect. Can you still hear me?
Yes.
Chat. Okay. Now I can see the chat room. Perfect. So let me see your questions. The hidden state, it's a state of the unit that you will use to build the output. It's just the hidden, it's just the name. This is the first question that I found. Dense and sequential in Keras. Okay, dense is the name of a layer that is fully connected, each unit with the following layer. So dense means that, and sequential in Keras is the way that you start to define your model. You can, you will see it in a minute, but you can start to define a sequential model and then put whatever layer you want. Okay, the rest can see the slides. Was some problem with the people who could not see the slides. Okay. Here, someone asked me, instead of an image, can we feed neural data such as sequence of time stamps to the convolutional neural networks? The answer is that you can feed to a convolutional neural network whatever data you want, but the idea, actually, a lot of people is trying to use convolutional neural networks also to analyze sequence, but I think I don't know too much about it, but I know that people is doing it. It is something that is new. I recommend to use recurrent neural networks to study sequences. But for instance, let me give you just an example. Let's say that you are interested in analyze speech or sound of, let's say, neural data that you have in a series. So maybe just something that I saw, you can plot the sequence like a figure in fixed value of length, and you can analyze that as it was a 2D imaging. So it may be possible, but you have to be very careful for the size of the data that you are processing, because when you use convolutional neural networks, you have to have a fixed value of the length for the data. Which part of the convolutional neural networks you train? So you train all the weights in the network. Sometimes you can download a pre-trained network and then you just train some part of the weight. But in general, if you are starting from scratch, you train all network weights. While using the maximum value during the pooling instead of the mean. Okay, because this is the operation called max pooling. There are other operations that you can perform with pooling, but uh, I think it is common from the convolutional neural network that are built in layers to use max pooling as a very useful layer to be trained. Will convolutional neural network help segment gray matter with matter and CSF from MRI data? I think it should be able to do that, but I don't know how much data you have that it's already separated, because please remember that you are applying supervised learning, so you have to have sets of data that you know how it behaves. So perhaps if you want to say that some part of an image are different, you have to present that information to the network in some level. So it could be used, in fact, there are people that it is using to separate different density levels on data, but you have to work a lot to define which is your data set and how you will use the information that you already have. Because neural networks are very useful tools, but you need to have data that you know how it behaves if you are using supervised learning. I miss where the weights are. The weights are the connection between the units and layers, and you need to train everything except that you have a pre-trained layer. We will see it right now in a couple of minutes when we study the hands-on. So I don't know if there are other questions. Please, if something was not clear, let me know. My English is awful and I'm very nervous because all of the issues that happen with the computer and the connection. So if something is not clear, ask me again. Okay, let's move on and see the last talk. And in this last talk, I will show you how to use Keras in our examples. And let's do that. And then we will move to the Colab from Google, and you will be able to use it and download it and copy to your computer or to your drive and do whatever you want with that. Okay, let's see the last talk. Let me share the window. Okay, share screen. Perfect. Can you see the screen? Just let me know that. Someone who said yes, and I will continue.
Yes.
Perfect. Thank you. Okay. I will give the chat window in the side. Okay, in this last part, it does not show. Okay. Here. present the slideshow. Okay, here. Well, in this last talk, let's see just how to use Keras. And again, if you want to download everything you need, here you have the links. Everything is very easy to install. If you want to compile it for your own architecture, it's a little harder, but you can also do it. And we already saw what is Keras. We know that it's very nice and easy to fast prototyping. It's very modular, friendly, and stuff. And something that I didn't say is that it is possible to be used with your CPU, but also with GPU. And if it is possible to install it for be used for GPU, very, very, very nice. But you have to take a look when you are downloading your proper version. So let's see how to build a sequential model again. So first of all, if you want to use neural networks, you have to be able to specify the input shape. This is the most important part, and for me, it is the harder part. Once you understood how is your data shape, then you can properly build your network. So the steps to build a model are the following. You have to specify the input shape. You have to specify the input shape and the way that your network is going to get the data and process it. Then you have to compile the model, and finally you train the model. In the language of Keras, it means fit the model. Fit the model means to train it. So a model compilation has three elements. You have your optimizer, that it is your algorithm that you will use to gradient descent. So then you need to choose your appropriate loss function or cost function. This is the function that your model will try to minimize. And what do you mean by input shape? I'm sorry. The input matrix, it's the shape, okay, because you could have a time sequence, you could have a categorical information. The input shape is not necessarily a matrix, it could be a tensor or a vector. So you have to understand very good how is the input that you are giving to your network. We will see it in an example. So, finally, the other thing that you need to compile a model is a list of metrics that you want to monitorize. So, which are the metrics that you can monitorize? You have a lot. For instance, it could be accuracy, or could be others. So, when you compile a model, you see something like this. You have your model that you previously defined, you put compile, and then you choose your cost function, your optimizer, that means your algorithm, and the metrics that you want to monitorize. Then, let's remember that Keras models are trained on NumPy arrays of input data. That means that, and also with labels, that means you have to take care of your data to be an NumPy array. So, what do we have? We have implemented convolutional layers, 1D, 2D, or 3D convolutional layers, special convolutional layers also. We have recurrent neural networks that are layers, and this is currently called vanilla recurrent network because it's a plain without any feature. Then you have a gated recurrent neural network, last term, short term memory, and you have another architectures. This is already implemented and you can pick it and use it in your model. So where are the which are the cost functions that you have? Oof, a lot of them. Mean square error, you have absolute mean square, percentage error, absolute mean square. You have a lot. You have just go to the library description and take a look that which are the cost functions that are available. And metrics also, you have a lot of them that you can use. And optimizers, as I said before, are our algorithms. You have stochastic gradient descent, RMS propagation, Ada grad, Ada delta, and you can go and see each one of the algorithms with the reference of the paper that describe the particularities of each method. So let's see an example here. So first of all, as we do with whatever Python library that we want to import, we import the libraries and the methods that we need, and then we start to write our model. In this case, first layer is a dense layer of 64 units, and then we put the activation function that we want. So let's see, here you will find the notebooks, and we will start right now to work with them in Colab. So I will share you my Google Drive link here in the chat room, just in case if someone miss it, it is in the website also. And we will start with one of the problems to understand how to implement everything that we talked just now. So please tell me if you missed something and you want to see something in more detail. And in the meantime, I will open in everything that we need for the collab. So please write whatever you need. So I will go and share screen. It's not. Okay. Because it closed when I was trying to. Okay. Okay, just give me a minute. I will open the exercise. Let me see if there is some questions here. Ah, thank you so much, Soledad. Thank you so much. So at the bottom of the website, you will find the link. Thank you so much. So now I will share the. Take some time, share screen. So you will see my screen in the Chrome session open. Please let me know if you see it. Could you see my Chrome window?
Yes.
Perfect. So now I am opening the exercise that it's called first Keras exercise. And as you saw before, I went to the top and I asked Google to open it with Colab, and it's as easy as I showed you before. Please let me know if you can do the same then in your computer. Otherwise, we will take care of it, and I will show you how to do it. Okay? So, if you open the code, as I did it here, you will see that you have something here that says connect, and then you have a notebook that I show you. And here, the first thing that I will do is to import the basic libraries that I will use along the tutorial. So here I'm using IPython, NumPy, SciPy, Matplotlib, and scikit-learn. I only have a link to GitHub. Okay. Let me do like this and like that. Can you open it? It's supposed that you have a... Otherwise, here... It works? Oh, perfectly. Perfectly. Okay. So, as I said before, here we have the libraries that we want to import, the basic libraries. Something that I do when I'm learning is to print a version of each program that I am using. In case that I have some problems, I could go to Stack Overflow and put the appropriate name of the version of the program. So in the second step, just printing which are the versions that I'm using. This line should be, sorry, I missed it, print on Py version. Because it is, okay, I didn't see it, it is import. No, it is not. It is not because I imported without the name. So it is NumPy, just in that level. Later you can import it with the proper name. You can, because in Python you can import libraries like this, or you can import libraries like this. Look at this. Sorry, NP. So since I didn't do it, it's like this. It depends on how you import the library. So let's see here. Then I will use some particular analysis tool from scikit-learn. So I'm also importing them. And if you do it like this, you will be able to run it also in your computer. Probably you need less to run it here. So I will go here and press Shift and Enter. And it is running. You go here and set connected. Sorry, it is in Spanish. I'm just noted. I don't know why. But it's starting. And then you will see that it says connected. And now it shows you how much RAM and how much disk are you using. This is the data that gives you and the engine that it's using. So now it shows you the data you want, and then you can move here. Sorry, here. And then we can take a look to the iris dataset. So here, iris dataset is a set that is made of plants information of different species, and you have labels on the species and data from them. So I want to use this dataset because it is very easy and nice, and it is used also for benchmarking and to learn and to solve exercises. So if we use this, let me show you, we can print some names of the features, and also we can print some data on the dataset. So let me press here, and now we have a lot of information here. We have a lot of information regarding the data set. That is very nice. And now we will work a little more on it. Previously, to go to the neural network, just to show you which is the use that we perform to it. So, oh my God, sorry, I don't know why, I have a mistake. I already ran it yesterday and everything was working, but I know why, because I took out the NP and I'm using it. Sorry. Let me just put this, import NumPy as NP. Okay, now it will work. Okay, perfect. Prints on the data, perfect. It runs. Okay. Okay, and now using the features that I described before, I want to plot the data of each species just to show you that it can be separated using some of the features, like the width of the plant, sepal width of the plant, or the sepal length, such as here. So if we go and run it, we will find some of the features that allow us to separate in different clusters the data. So we have data that is labeled, and we want to separate the data with some algorithm. Here we do not need to perform very complex neural network algorithm, but I will do it anyway because I want to show you how you write down this information. So here we have another network visualization, very nice and easy. And then let's use whatever that we know about this data set that has labels and features to create a model, a very simple and nice model, in this case a sequential model, and we will use our model to classify the data that we have. So I import the necessary libraries and I create a custom model in this way that we are defining here. So we will add for each of these nodes and sorry, I will create a model. Sorry, I forget about it, but I will create actually 3 models. So I will create different models, each of them that I will use in the bottom part, and I will train all of them because I want to compare the results. That's the idea. So here I am not creating one model. I'm making this to create as many models as I want, and then I want to create the models with different layer sizes. So in this case, you will have information not only of how to create one model, but also how to use the comparison between them. So in this case, for all the models that I create using this part of the code, and then the implementation of it here, I will summarize each of them. So we have in the model that I call 1, here, a dense layer, the first dense layer that has 8 units, and the second layer that have 3 units. Why the second layer have 3 units? Because I want to classify 3 species of plants. And then the same, I want to create a model, but with another layer, another hidden layer. So we have a deep learning model, let's say, where I have 8 units in the first layer and 8 units in the second layer. And of course, at the end, the layer that allows us to classify the species. And finally, I am performing a model that has 3 layers. So the code that I had before allow us to create models with different number of layers. Then you can go and play and change the number of layers if you want. You can add more layers and try to see what happens when you try to train them. So now that we have our 3 models that are different, we have to train the parameters. So for the models that I described before, for all the models that I described before, I want to train them. So I will train them and I will take a look to some of the parameters. So for the first model that I trained, it took me a little time because the model has only 3 layers. Here is the model 1 here. And if you take a look to the other models here, I train the first one here, the second, and the third model. And then now we have the 3 models, we want to compare them. So I will plot some of the metrics values, and I will compare metrics of each of them here, the loss, but the validation loss and the validation accuracy of each of the models. And then I will use metrics to choose which is the model that I will keep. Just an example. So you can go run this code and obtain 3 neural network models to classify the plants in the 3 categories and choose which is the model that has the better metrics. Finally, we can go and print some of the data here, and we can choose and try to see if our prediction of the model is working good. So, I'm sorry.
Este es el resultado principal de la búsqueda.
Here. Sorry, I cannot find it. So, I have my data that I already tried to select, and here is the part of the code that I use to predict the results of the model. So I took some of the data of my plants, and I want to predict how well I did with the labels. So I know it's a lot to see in one tutorial, but you will keep the code and you can play and still ask me all questions that you want. So I don't know if it was clear, but I wanted to show you this one, the one that is called first Keras exercise allows you to play and compare 3 different models to train them and to use them to classify species of plants that have flowers. If you want to take a look, you can go and put in Google iris dataset, and you can see also the colors of the plants and stuff to see what is this thing about. So please let me know. I will stop sharing this part, and I will share now the second tutorial that is specifically how to use really good Keras to classify the digits of the MNIST dataset. So questions till now? Please don't hesitate to ask me. It is hard to present like this, but I choose cross entropy function because it's the appropriate one when you are training networks for classification tasks. Cross entropy is the one that you will use. If I was using networks to make some predictive models and not classification, I will use, for instance, the mean square error function. Okay, let me open the next one. Is the one that's called Conv from Convolutional. Again, I will open with Colab. When you go, yes, of course, you need a validation set, but in this case, since I was using it for just for plain, I didn't choose that. You can use a testing set. Validation set is actually for that. It's for comparing models, actually, yes. Sorry, let me... I want to share here. Can you see the window? The code window, please let me know.
Yes.
Perfect, thank you so much. So let's see this example. The idea is that I want to work again with Keras. Now this part, you can ignore it. It's some part of configuration, but it is not here. It is not needed to use it in Colab. It was needed for my computer. And let's see, let's start from here. Okay. So I need to, yes. Of course, I will. Thank you. Of course, here. Can you see? Please let me know if you see it, okay? Okay, now let's continue. So let's start by taking the data set that we want to use. So in this case, is the MNIST dataset, and we have it everywhere, but I'm importing it from TensorFlow. So I'm asking from TensorFlow datasets to load the MNST. So here I cannot see it, but here, as I have a TensorFlow imported, I ask it to open it and split it in a training set. And just to show you an example, you can take one of all the data set and see the shape of it. Actually, you can print it and do whatever you want when each of the elements of the data set. Remember that the data set is an imaging that it's in black and white, and a label that represents the number that is drawn in the image. So we take the data set and we take a part that we use as a training set and a part that we will use as testing set. If we want to print the information of the data set, here I print one of the images information, and it's a 28 per 28 imaging, one element that has one label. So we have the size of the imaging and the feature that we have, that it's a label. Then if we print all the data set, we will see the size of it, and then we make some arrangement for the images to regularize the size. I'm normalizing the size of the images here, and then I'm printing the shape of the images. Here, when I said images, I said the full data set. So I have, for the training part, this amount, and for the testing part, this amount. Please remember that the training part is a very, very large data set. and the testing part is a smaller data set. So now, why is important to normalize the images? No, in this case, it is because I want them to print them and to work with them a lot. So I normalize them to this size, and I will see later that I print some of them. This one, the dimension 1, because I think it is, you have this amount of data, this is the size of the imaging, and this is the label. So remember that you have the image, it is a tensor. You have a imaging size, and then you have one more dimension for the label. Your full data, okay, perfect. So now I will import the layers that I will use in the model. In this case, I will use a sequential model, and I will use convolutional 2D layers, max pool 2D layers, dense and flatten. You will understand now which is one of the layers for. So the first is our sequential model. The first layer here is a convolutional layer with the preset number of filters that I define here. This is the filter size. This is then the pooling size. And these numbers are not chosen at random. I took this as an example because the quality of the classification will depend on the experience and the things that people already prepared before. So I recommend to take a look of how many filters do you need, how is the filter size depending on each task. It is not something that I can try at random. You can move a little around, but these are very much the values that you have to take if you want to make it work. So, as I said before, you have a convolutional layer, then you have a max pooling layer to reduce the dimensionality, and finally, you have a flattened layer and the dense layer, that is the one that will give us the classification of the digits. Remember that the task that we are training the network for is that given a written and handwritten digit, we want to know which one of it is it. So we have 10 of them, from 0 to 9. Now, we have our model, we have to compile it. So remember, we define our model here. Now we compile the model here. We compile the model as I showed, sorry. And then I work here some with the labels because I have to redefine something to make it from the proper size for the fitting. And here I will use, I will fit the model. Oh, sorry, I moved it. Here, I will fit the model. Here, the epochs is the number of iterations that I want to define. And here is the validation. Here I put the validation data set that I need. I'm hearing some noise. I don't know if there's any question. Okay, I will continue. So when you train the model, you can save it. You can try to train it with different epochs and compare it. And you can save here the model as an H5 file, or you can use other kinds of formats to save the model. So here, when you save the model, you are saving the values of the matrix that contain all the parameters, all the weight parameters of each layer and the configuration. So now we will use the model. Sorry, I again move here. Okay. So we will use a model to predict some of the handwritten digits. Here I took this is in Python, you have a list, and I'm saying, please give me the 5 elements of the list, the first 5 elements of the list. Here, the 5 elements of the list have the labels 72104. I already know that because it is a testing set that I can see. So the idea is that as I know that they are the current values, I want to see if the prediction is according to the values that I get. So I use the model to predict the imaging values, and finally I get that the prediction, sorry, it matched, sorry, the value of the labels that I already get. So we can also go and print that it is true that the labels were properly put in the data. So you can print some of the imaging here, and then you have a full model. So you have the definition of the network, you have the data treatment for this kind of images, you have the training of the model, the saving of the model, and also you have the testing of the model with some printing of the images. So I think this example is really nice because you can go around and see all the steps, and you can go and play and change some of the information here. And you have an example of convolutional neural networks currently working. So I think this example is very nice. If you have questions, please do not hesitate, write it in the chat room. And now I will also leave this example for everyone who wanted to download it and use it. And also I want to show you one last example that I did. Yes, I have a question. Building the model. A question for building the model. If you have multiple convolutional neural networks layers, could you explain a little bit what would be the input size to the next layer? Would that be numbers of, yes, it is related to the numbers of the filters, but I think when you are here, I will show you again the convolutional. Yes, you can reuse it. Yes, you can reuse the model, and you can pre-train models and pre-train layers and use them. I don't know about this format. I use this 5. I think it's like this. I'm sorry, I have dyslexia, but I think it's like this. This is the format that I use, and it is very easy to open in Python for different sites. Maybe you can check the documentation. Probably it says that if you can use PKL format. I don't know that format at all. So sorry about the convolutional layers. I think when you are using multiple convolutional layers, here you can predefine this number using the following layer, the previous following layer. So you can get track of each of the numbers probably automatically. So I think it is better to define all the size of the convolutional layer with respect to the size of the max pooling and stuff, to be very careful. The input of each layer is equal to the number of feature map. Yes, you have to be careful to that. Okay. Of course, if you make a mistake, the model will not compile. So you can go around and see if you make a mistake in the sequential definition of the model. That is very useful. Every time that you have a mistake, you can go back and see. It is very intelligent, and it says whatever mistake you made in which layer is, it says that the number does not match the size of the input and stuff like that. So it is very easy to follow. So any more questions? Can I move to the last exercise? Let me know. Okay, I will close here. Oh, okay, perfect. Okay, I will close this one. Stop sharing, and I will share the last exercise. It's also in Colab. It is very, very easy. Okay, here is the link. We put it on the chat window. Here you can go and open it, and I will share the screen. I will share the screen here. And I must say thank you for your patience during all the presentation. This is my first time presenting in this way, so okay. Please let me know if you can see the last exercise. Actually, it is a very easy exercise, and it was perfect. Thank you. It was inspired in because I teach digital electronics, and it was inspired on that. I want to teach a network to perform the XOR gate operation. That means that whatever the binary inputs are equal, the output must be 0, and when the inputs are different, the output must be 1. So here it is very, very, very simple example for training a network. In fact, this function is not necessary to use so large network as I used, but just for fun, I did it. So we have the data here that we prepare. So we have very, very clear training data. It's our sets to the input. Here you have 4 different expected value of the output. They are ordered, so this one is the output of this one is the output of this one, and so on, so far so on. And now we will generate and compile our very, very simple model. In fact, you can do this with less units. You can then go and play. So we define our model. We add our layers here, sense layers. It means, remember that it means every of the units are connected to each other. So we have one output. We have only one output. Why we have one output? Because we want only one state. For each set of numbers that I put in the input, I get one output state, 0 or 1. So I compile the model. The cost function in this case is mean square error. Why is this? Because it is not a classification problem. It is a prediction problem. What do you use? No, I choose whatever function I wanted. You can actually try to do it with different functions, and you will see that it works with almost all of the nonlinear functions. You can go and play and we'll see that it's not a particular function you need to add, just as an example. Okay, I choose as a cost function mean square error, since I have to make a prediction over the data. The optimization algorithm here I choose is ADAM, and I choose to follow this metric, but not for any particular reason. So again, we trade our data, we define our model, and now we train the model. So I train the model, but I exceed because a lot of instances of the model, I don't know why I did that, but you need much less to obtain a very good accuracy. So now I want to test the data, but since here the testing data is the same as the training data because I don't have any more because it's very, very toy model, I'm able to print some of the metrics that I follow. So I can print the training data, the target, and the model prediction. Here you will see the model prediction as a number between 0 and 1. And here you will see the model validation. So that's all. It's a very, very short example. I didn't start with this. I prefer to start with one of the plans because it has a lot of information on how to use scikit-learn if you want to take a look. You have, sorry, I'm hear some sound. Do you want to ask me a question? I don't know if you want to ask me some question.
I will mute all of you again. Sorry, and then Cecilia, you can unmute yourself.
Okay. Here I am. Perfect. So here we have 3 examples of how to apply neural networks. I have some additional examples of how to apply recurrent neural networks if you want to take a look further. But I think today I present a lot of information. I think Keras is a very, very nice way to implement neural networks models. And basically, I wanted to present you the tools and the places where you can go and pick up the information you need to start to using it in your own models. I have another question here. What happened with the lesson sample? Why was one of the loss function increasing? Because I took here, because I use, in some point, I exceed, you mean in the training or in the plot? Here. Here, because I did not choose the proper metric to follow. You have to be, another thing, another message is that you need to properly choose the metric that corresponds to the kind of problem. So since this was a very toy problem with not training data and testing data, maybe some of the metrics have no sense to be used. So the idea is that this is the take-home message also. You need to take a look, which is the metric that represents better the model fitting, and which is the one that you have to follow. That's something important. And another take-home message is that please take a look to the already implemented examples. To implement recurrent neural networks, it is not easy from scratch, but if you take the libraries and the work that was done for the thousands of people that have been working on this a lot, you can implement it in your own models. Okay. Do you want to see something on recurrent neural networks? I will share to you some tutorial that I have, but I use them not to for machine learning. I'm using them in Keras to model dynamical systems. So I use very basic version of recurrent neural networks. If you are interested, then we can talk and I can share you some tips and say to you which are the best practice on this. So please write to me an email or contact me, please, and we'll show you something more. I don't know why you need to use them. Maybe if we discuss further in which field you need to use them, I can go on and give you some more material. I would be interested in having some reading material as well. I will do that. Okay. I will share also the slides and all the data. So please email me and I will share everything that I have. And if you go in the slides, you will find at the end that I put some information on another course that I took myself, and it's very useful. And I put some links to download information. So please go take a look. So, oh, okay, thank you so much. And thank you for being so kind and patient. It was very hard for me. It was not the way that I was expecting to present this tutorial. So thank you so much. Uh, okay,
Thanks to you for
so
an amazing tutorial.
oh, thank you so much for being so kind. It was really, really, really hard. Okay, I will stop sharing the screen. And I'll be here some minutes more if you have some comments more. Otherwise, you can leave the meeting. Okay, thank you. Thank you so much. I will save this as a screenshot to show it to myself when I was having imposter syndrome.